Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 2 on congruent triangles. Now, I know we've talked about congruent triangles a lot so far, especially in Unit 2 when we were working with transformations and rigid motions. And in fact, we pretty much defined congruent triangles using rigid motions. Today, we're going to hammer on congruent triangles a little bit more because they are really going to form the basis of everything that we do from now on in Unit 3 and for much of what we do for the remainder of the course. So let's get right into it and discuss congruent triangles. A triangle is congruent to another triangle if there exists a sequence of rigid motions that could map one triangle onto the other triangle. Because of this, congruent triangles are the same shape and size. So literally, when you first learn about congruent figures, specifically congruent triangles, it's, well, congruent triangles have the same shape and the same size. Now we're literally saying a triangle is congruent to another one if there exists a rigid motion, right? A translation, a reflection, a rotation, or a sequence of those that maps one figure onto another. So let's just talk about this really quick with exercise number 1. Given the grid shown below, A, describe a rigid motion that would map triangle ABC onto triangle A', B', C'. All right, cool. So I'd like you to write down, as specific as you can, one of the rigid motions, and it's just one, it's not a sequence, you don't have to do 2 or 3 of them, right? Just one that will map triangle ABC onto triangle A', B', C'. Go ahead and pause the video and see if you can figure out what that is at this point. All right, well, it's probably pretty obvious, right? It's going to be a translation that essentially maps, right? That maps point B up to point B', point A up to point A', point C up to point C', right? All of those vectors are the same, and we just want to slide triangle triangle ABC up to triangle A', B', C'. So it's a translation. And we just want to talk about what the movement is left, right, up, down. So a translation by 1, 2, 3, 4, 5, 6 by this translation 6 units right, and what do we have? 1, 2, 3, 4 units up. All right? So a translation of each of those vertices 6 units to the right and 4 units up will map triangle ABC onto triangle A', B', C'. All right, letter B. What can you say about the lengths of segment BC and segment B', C'? Why? Well, go ahead and write something down. Okay, well, hopefully what you'd say is the lengths are the same. I feel like I shouldn't even try to write over the red anymore. I'm just going to accept it. I'm just going to go with it. I'm just going to go with the red on this. All right. Now, why, right? Well, for why, you could really give 2 completely acceptable and more or less equivalent reasons, right? One reason would just be a rigid motion or a translation preserves distance length. So in other words, right, the length of B', C' is the image of BC, and therefore they've got to have the same lengths because it was a translation, and a translation is a rigid motion. Or you could say, because BC and B', C' are corresponding sides of 2 congruent triangles, they must be congruent themselves. I think I'm just going to go with the first one right now, which is that translations are rigid motions and rigid motions preserve length, right? So really, the length of any image will equal the length of its pre-image under a rigid motion. Now here the rigid motion was a translation, but if we had a reflection or a rotation, that would also be true. All right, let's keep talking about congruent triangles. Exercise number 2. In the diagram shown below, D lies on BC such that segment AD is the perpendicular bisector of segment BC. Letter A. What information does the given of, quote, AD is the perpendicular bisector of BC tell you? Mark this information on the diagram appropriately. All right, so what I'd like you to do is go ahead and answer that. Well, the fact that AD is the perpendicular bisector of BC really tells us 2 things. First, let's just take the bisector portion. I know that comes second, but I'm doing it first anyway, right? That tells us that BD must be congruent to CD. They've got to be the same length. That's the bisector portion. The perpendicular portion, of course, tells us that these 2 angles must be right angles. So in other words, angle ADB and angle CDB are right angles. Right? They're right angles. Simple enough. Letter B. What rigid motion would map triangle ABD onto triangle ACD justify? And don't worry about that blue triangle sitting there. We're going to get rid of it in just a second. So why don't you go ahead and figure out, should be obvious, I think we've done this one a couple times, what rigid motion you could use to map this triangle ABD, and why don't I just put it up there so that you can kind of see it nicely outlined in blue. I want to somehow map that triangle onto that triangle. Go ahead and pause the video now and not only technically list what the transformation would be, but see if you can justify it as well. All right, well, hopefully you said a reflection across segment AD. And you could also say line AD, that would be fine, it doesn't really matter. A reflection across either segment or line AD. Now, by the way, let's take a look at that, right? If I click on that triangle and I do a flip up, down, right? Then it maps it directly onto ADC. Now, we've done this justification a few times, but let's do it again. Whenever you justify that a transformation will map one triangle onto another triangle, what you have to do is explain how that transformation maps the 3 vertex points of the one triangle onto the 3 vertex points of the other triangle. Now, 2 of the 3 vertex points are easy, as they always are in this particular one, point A and point D. Point A and point D lie on the line of reflection, and therefore they get mapped to themselves. So let's start with that one. A and D get mapped to themselves. Whoops, themselves. All right, and I gotta leave myself enough room here. Actually, let me just shift this down a bit. Hold on. Let me unlock. I'm just gonna shift this down to give myself a little more room to write. All right, lock that back in place. Because I really wanna put this, A and D get mapped to themselves because they lie on the line of reflection. Or I could have just said it more succinctly, because they lie on line AD. All right, so then the question becomes, why does point B get reflected to point C? And that is because, yet again, AD is the perpendicular bisector of BC. All right, so, oops, point B maps to point C because AD is the perpendicular bisector of AC, right? And that's, again, goes all the way back to the technical definition of what a line reflection is, right? A line reflection always means that what I have is that the line of reflection is the perpendicular bisector of the segment that connects the pre-image point to the image point. And whenever we have that scenario, then that means that if we reflect that point, or across that perpendicular bisector, it will land at the other endpoint of the segment. Something that's starting to become painfully obvious now. Now, letter C. Write a formal congruent statement for the two triangles. All right, so let's talk about this, right? So we're going to see a lot of this in the coming lessons. Triangle ABC is congruent to triangle DEF or whatever, right? Now, really, what I'm going to do is I'm going to just really quickly draw the two congruent triangles sitting beside each other, right? So these are my two congruent triangles. I'm just taking my triangle ADC and I'm sort of like writing it right here. So what I need to say is I need to say that triangle ABD is congruent to triangle ACD, right? ABD is congruent to ACD. I need to make sure that the order of the vertices here corresponds to the order of vertices here. I can't just throw them down in any order. I can't be like triangle ABD is congruent to triangle CAD. It doesn't matter, right? I'm just grabbing the letters. No, right? This A corresponds to that A, this D corresponds to that D, and this B corresponds to that C. They have to be in the same place. Now, I could have said triangle BAD is congruent to triangle CAD. That would be okay. But once I set the order of the vertices in one statement, it has to be the order of the vertices in the other. Now for letter D. Write down all corresponding congruent side and angle pairs for the two triangles, right? So because these triangles are now identical, all of the corresponding sides and corresponding angles also have to be congruent. For example, right? AB must be congruent to AC, right? That is one congruent corresponding side pair. Let's do a corresponding angle pair. This angle, which is angle BAD, must be congruent to this angle, which is angle CAD. Right? So those are corresponding angle pairs. What I'd like you to do is write down the remaining. You'll have two more pairs of corresponding sides and two more pairs of corresponding angles. I'd like you to write them all down with the congruency because they must be congruent because the two triangles are congruent. Go ahead and do that. All right, I'm going to do the side pairs first. Let's go with this one, right? So that's segment AD must be congruent to segment AD. That's not very interesting. Segment BD must be congruent to segment CD. Now let's get some angles out there. Let's do this angle. Angle A. Whoops, let me just kind of scroll up here. Angle ABD, all but done, is congruent to angle ACD. And finally, let's do this one. Angle ADB is congruent to angle ADC. There we are. Now, this goes to a really important idea with congruent triangles, and let's talk about that next. An extremely important, not just an important idea, an extremely important idea. Let's take a look at it. Corresponding parts of congruent triangles are congruent, what we will abbreviate often in this course as CPCTC. Since two congruent triangles are identical in size and shape, parts, which are just the sides and the angles, that correspond, they're in the same place on the two triangles, must also be congruent, which means they're either the same length if they're side lengths, or they're the same degree measure if they're angles. All right, so this is an obvious idea. An obvious idea. You know what I mean? It's like, have you ever been in one of those sort of like subdivisions where there's a bunch of houses that look exactly the same? You might even live in one of those subdivisions. I've often wanted to because I love the look of the houses. But the houses look literally identical, right? They're congruent houses. And you could make the argument that the front doors on two identical houses must be identical because they're in the same place, right? Their corresponding front doors on identical houses must be identical. It's the same way here. If I've got two angles in the same place on two identical triangles, well, then they have to have the same degree measure. Or two sides that are in the same place on two identical triangles, they have to have the same length. Okay, so let's take a look at exercise number 3. If triangle LMN is congruent to triangle RQS, measure of angle MLN equals 82 degrees, measure of angle MNL is equal to 46 degrees, measure of angle NML is equal to 52 degrees, and MN is equal to 8, do the following. Letter A. To the right, draw a rough diagram of the two triangles. Okay, now here's the thing, all right? If I've got two triangles that are congruent and I want to sort of just get a feel for them, I do not need to make these triangles look perfect. What I do want to do is draw two triangles that aren't equilateral or isosceles. I don't want that, okay? I don't want to be like, right? I want to make sort of what I call two generic triangles, okay? Here's a generic triangle. And then what I'd like is another generic triangle that looks as close to it as possible, okay? So that I can kind of then like judge it. Now, again, I don't have to make everything perfect, okay? I'm going to do LMN. Now, I have to make sure that wherever R is on the next triangle, it's in the same place as L. And wherever M is, it's in the same place as, wherever Q is, it's in the same place as M. And wherever S is, it's in the same place as N. Right? The vertices have to correspond to the same locations, okay? And that's letter A. Let's take a look at letter B. Label the angles of triangle RQS with their proper measures. All right, well first, let's put in the angles of LMN. Now we know that measure of angle MLN is 82 degrees. MLN is 82, which means QRS is 82, right? We know that MNL is 46 degrees, which means QSR is 46 degrees. And we know that NML is 52 degrees, so we know that SQR is also 52 degrees, right? Corresponding angles in congruent triangles have to be congruent. Finally, let's take a look at letter C. Which side of triangle RQS do you know the length of? Label. All right, see if you can figure this one out. Well, we know only one side length, and that's MN, which is equal to 8. Now I can label that right here, but that means that QS must also be equal to 8. And it's got to be equal to 8 because those are corresponding sides on two congruent triangles. Simple idea, right? If I have two triangles that are identical, then parts that show up in the same place on the two triangles must also be identical. CPCTC. Corresponding parts of congruent triangles are congruent. CPCTC. All right, now let's talk about congruent triangles in complicated diagrams. Very often we will work with more complicated diagrams that have congruent triangles within them. So let's play around with that a little bit in exercise number 4. In a parallelogram, when two diagonals are drawn, they bisect each other. We're eventually going to prove that. With AE congruent to CE and BE congruent to DE as shown. answer the following questions. Letter A. If triangle AEB was rotated by 180 degrees about point E, what triangle would it be mapped onto? Make a formal congruent statement. Now I've already kind of outlined a little bit in blue triangle AEB. And I'm saying if you take this triangle and you rotate it 180 degrees about point E, what triangle would it get mapped to? And then because it would get mapped to those two triangles through a rotation, which is a rigid motion, we would know the two triangles are congruent, and then we should be able to say, this triangle is congruent to this triangle. Go ahead and do that if you can. All right, well, let's actually rotate this thing, right? So here we go. I've got that triangle, and watch as I rotate it, right? As I rotate it around, right, that is going to be a 1/2 turn or a 180-degree rotation, and notice what happens. It gets mapped onto this triangle down here. Now notice how I put that. It gets mapped onto this triangle down here. I haven't named the triangle yet, okay? So what triangle would it get mapped to? Well, AEB, right, would get mapped to the triangle down there, but I want to make sure that I have the right congruent statement. So which letter goes with which? In the last situation, it was pretty easy, but let's very specifically pay attention to where A goes, right? Remember, A is right up here, right? And A gets mapped down to C. Right? So triangle AEB, A gets mapped to B. Notice E doesn't go anywhere. It gets mapped to itself. And then kind of by default, if you watch where that vertex that was at B goes to, it gets mapped down to D, right? And that makes total sense, right? Because this segment is the same length as this segment, and D, E, and B are collinear. So if I rotate B 180 degrees around E, it's going to land on D because those segments are the same length. And likewise, if I rotate A 180 degrees around E, it's going to land on C because those two segments are the same length, meaning that triangle AEB is congruent to triangle CED. All right, but there's more congruent triangles in this figure. Letter B. If triangle AED was rotated 180 degrees about point E, what triangle would it be mapped onto? Make a formal congruent statement. All right, same song, second verse. Why don't you go ahead and try that? All right, absolutely the same idea. Let's go ahead and take a look at that mapping, right? Again, keep in mind, watch where A goes, right? If I rotate it around, eventually, that 180 degree rotation means it lands there, right? And where did that A go? Well, it got mapped again to C. Where did that D go? It got mapped to B. So this triangle now, what am I calling it? AED gets mapped onto CEB, right? So I can say triangle AED is congruent to triangle CEB. And we can say that again because those rotations, right, they're rigid motions. I mean, you could see it, right? That the shape and size of that triangle didn't change as I rotated it around, and it landed on triangle CEB. Now what's cool, right, is now we can start, talking about, there it happened again, Joey. We can start talking about angles, and this time it was Ted Cruz. It's always some Republican coming out. It's weird. I don't get it. Anyway, let's talk about letter C. Windows 11. Based on letter A, what angle can you say is congruent to angle EAB? Mark the two congruent angles on the diagram. So I've marked off on my diagram angle EAB, right? What angle has to be congruent to this one based on letter A, right, way up here, where we learned that this triangle was congruent to that one. All right, C, mark the two congruent angles and then write down a congruent statement between the two angles. All right, well, let's do the rotation again just to see it, right? Keep an eye on that angle. right? That angle there gets mapped down to that angle there, right? So angle EAB is congruent to angle EAB is equal to ECD, right? ECD. And the two congruent angles are this one and this one, right? Those two angles have to be congruent. Let's take a look at D, which is very similar. Based on B, what angle can you say is congruent to angle BCE? Mark the two congruent angles on the diagram. Again, I've already marked off angle BCE. You figure out what angle it has to be congruent to. All right, I kind of wish I had marked this one off with a double angle mark. We'll do that at the end. But again, very simple. Watch where that thing goes. When I rotate it, right, it ends up being right up there. So angle BCE is congruent, BCE, is congruent to ADE. All right, simple as that. And again, what I would do is on your diagram, because you don't have 1,000 of these like I do, I would mark it with a double angle mark. By the way, if you've been like kind of noticing, right, both of those pairs are what we call alternate interior angles created by parallel lines. We'll come back to that in Unit 3 eventually. Now, final issue, letter E. Make an argument for why both A and B together allow you to conclude that opposite sides of this parallelogram must be congruent, i.e. they must be the same length. So why is it that AB must be the same as length as CD and why BC must be the same length as AD? They have to be, and it can't just be because they look like they are, okay? That's not allowable. We've learned something in this problem that will allow us to say why that's true. Pause the video and see if you can write something down. Well, first, let's talk about those ones with the single dash mark. Why does AB have to be congruent to CD? Well, because that triangle is congruent to that triangle, and those are corresponding sides, right? So AB is congruent to CD because triangle ABE is congruent to triangle CDE, right? And likewise, right, AD must be congruent to BC, right? Because triangle AED is congruent to triangle CEB. All right, so AD is congruent to BC because triangle AED is congruent to triangle CEB. I'm going to leave the red, going to leave it, not fighting the red anymore. All right, so we learned quite a bit about parallelograms just from being able to do those rigid body transformations, those rigid motions. All right, so let's summarize. Now, we didn't see particularly a lot that was new today. We already knew about congruent triangles. We already knew how to define congruent triangles in terms of rigid motions, right? Today we worked a little bit more on like formal congruent statements, i.e. this triangle is congruent to this triangle. And we worked a lot with this principle called CPCTC, corresponding parts of congruent triangles are congruent. In other words, things that are in the same place on two identical triangles are identical themselves. All right, that's going to be a bedrock principle throughout this unit and hopefully one that makes just complete and utter sense. We're going to see a lot more of it in our upcoming lessons. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.